Today we're going to look at a sketch of the original proof showing that pi is irrational, and this is due to Lambert. And the first thing that we'll do here is find a continued fraction for the tangent function. And we're going to do that by using the Taylor series for the sine and the cosine function. So I'm just going to assume that you know those. Those are well known, and you learn those in like a second semester calculus class. So we've got cosine of x is equal to, well, we're going to set it equal to f sub 0 of x for our notation. And then the first few terms go like 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, so on and so forth. If we were to write it all as one thing, it's the sum as n goes from 0 to infinity of minus 1 to the n over 2n factorial times x to the 2n. And then similarly for sine of x over x, which we will write as f sub 1 for our notation, that'll become the sum as n goes from 0 to infinity of minus 1 to the n over 2n plus 1 factorial times x to the 2n. So we're dividing sine of x by x just because it helps with our calculation. Okay, so now I want to introduce a family of functions that we can recursively build out of f0 and f1. And the first step toward that goal will be to look at the difference f1 of x minus f0 of x. So let's see, we can put that together pretty easily. So that's the sum as n goes from 0 to infinity of minus 1 to the n. And then, well, let's see, we'll have 1 over 2n plus 1 factorial minus 1 over 2n factorial times x to the 2n. Because notice we've got x to the 2n here, x to the 2n here, minus 1 to the n in both of them, so that we can factor those out. So really we're just taking the difference of these factorial parts, if you will. Okay, so now what I can do is observe that this second term can be written as 2n plus 1 over 2n plus 1 factorial simply by multiplying the numerator and the denominator by 2n plus 1. So that's going to give me the following expression. So I've got my sum as n goes from 0 up to infinity, minus 1 to the n. And now this is going to look like minus 2 times n over 2n plus 1 factorial times x to the 2n. That's just from taking the difference after, putting those two fractions together. Now I'd like to observe that I can do a couple of things here. So first of all, I can take this minus and turn it to a plus if I change this n to an n plus 1. That's pretty clear. Also, I can take this starting point of n equals 0 and change it to n equals 1. That's because the 0th term here is kind of obviously equal to 0. Next up, I'll re-index this sum, and I'm going to re-index this sum by replacing all of the n's with n plus 1. And that's going to shift my starting point down to 0 again. So that'll leave me with the sum as n goes from 0 up to infinity of minus 1 to the n. And now I have 2n plus 2 over 2n plus 3 factorial times x to the 2n plus 2. So I've got something that looks like that. But now I think it's going to be natural to factor an x squared out of that. So it looks like a power series in x to the 2n type terms like our first two. So if I do that, I'll have x squared and then the sum as n goes from 0 up to infinity of minus 1 to the n over 2n plus 3 times 2n plus 1 factorial times x to the 2n. You'll see what I did there. I took this 2n plus 2 and I canceled the 2n plus 2 term that was in the denominator. But I'm going to do one more thing before I maybe continue to the next step. And that is I'll observe that if I factor a 3 out of the denominator by writing this as x squared over 3, which means I need to put a 3 in the numerator right there, That means the first term of this series is equal to 1. So we can see that this is 1 plus a bunch of other terms. But notice that these two are also 1 and then plus or minus a bunch of other terms too, so it has the same kind of thing. Then what I'll do next is rename this whole thing f sub 2. So this will be my f sub 2 of x. So what I have here is f sub 2 can be defined in terms of f1 and f0. So in fact, I have f sub 1 of x minus f sub 0 of x is equal to x cubed over 3 times f sub 2 of x. And this is going to be with, we might as well do this kind of for completeness, f sub 2 of x is equal to the sum as n goes from 0 to infinity of 3 times minus 1 to the n over 2n plus 3 times 2n plus 1 factorial times x to the 2 times n. Okay, so now that we've developed this next power series that is kind of built off of our f0 and f1, let's maybe do a calculation to find f sub 3. And then after that, we can guess at a general form for instance, f sub k. We'll prove that general form before we move on to really constructing our continued fraction. So on the last board, we defined our f sub 2 function in terms of the difference of f1 and f0. And now what we'd like to do is continue that on and define our f sub 3 function in terms of f2 minus f1. So okay, let's look at that. So we'll have f2 of x minus f1 of x is going to be equal to, well, we have the sum as n goes from 0 to infinity. Then we'll have minus 1 to the n. And then let's see, f sub 2 looks like this. Let's observe that we can factor a 2n plus 1 factorial out of the denominator of both of these. So we might as well do that. And I'm going to put that at the end. So that's going to leave me with 3 over 2n plus 3 minus 1 times 1 over 2n plus 1 factorial times x to the 2n. So again, that's from factoring out everything we can factor out from both of those terms. Okay, nice. But next up, we'll observe that this thing right here will simplify nicely. And we can do that by finding a common denominator. What we'll see is that this is minus 2 times n over 2n plus 3. So maybe I'll put that in parentheses. That's what's happening inside of that parentheses with 3 over 2n plus 3 minus 1. So now let's maybe write that down. So we've got the sum as n goes from 1 to infinity. So I'm going to start that at 1 because notice my 0th term is 0 again. And then I'll have minus 1 to the n plus 1 by taking this minus sign and combining it with the minus 1 to the n. And then after that, we'll have 2n over 2n plus 3 times 2n plus 1 factorial times x to the 2n. So next up, we're going to do the same kind of thing that we did before, and that is shift our series by re-indexing n to n plus 1. That's going to shift my starting point back down to 0. So here I have the sum as n goes from 0 to infinity of minus 1 to the n. I guess it's really minus 1 to the n plus 2, but that's kind of clearly the same thing as minus 1 to the n because minus 1 squared is 1. And then here we'll have 2n plus 2 over 2n plus 5 times 2n plus 3 factorial, all times x to the 2n plus 2. Now I'm going to factor out an x squared just like I did before. And I'll be left with the sum as n goes from 0 to infinity of minus 1 to the n over 2n plus 5 times 2n plus 3 times 2n plus 1 factorial, all times x to the 2n, where I'm doing that same simplification that I did in my previous calculation, this 2n plus 2 will cancel down that 2n plus 3. But now I'd like to observe that the first term here is 1 over 15. So I'd like to factor that out. So that'll give me x squared over 15 here. And then I can put a 15 here in the numerator. And then this gives me my function that I'll call f sub 3 of x. Then maybe to look towards some sort of pattern here, let's observe that we can take this 15 and rewrite it as 5 times 3. And so what's going on here? Well, notice that my f sub 2 term had this 3 over 2n plus 3, and then the rest of it was essentially the same thing as f sub 1. And then my f sub 3 term has this 5 times 3 over 2n plus 5 times 2n plus 3, and then the rest of it, again, is essentially this f sub 1 term. Okay, so next up what I want to do is maybe summarize what we have for our f1, 2, and 3. We'll guess a general formula for f sub k and prove that that's the right formula. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up, and if you're not yet subscribed, consider subscribing, it really helps out. Okay, so via our recursion, we were able to build this f sub 2 and f sub 3 power series using f1 and f0 as a seed. Now, I'd like to observe that f sub 2 has most of the parts the same as f sub 1. Notice that it's got this minus 1 over 2n plus 1 factorial term, this x to the 2n term, but what is included in it now is a 3 over 2n plus 3. And then f sub 3 likewise has that minus 1 to the n over 2n plus 1 factorial x to the 2n, but now it's including a 5 times 3 over a 2n plus 5 times 2n plus 3. So I think that pretty clearly motivates us to guess the following formula for f sub k of x. So it looks like this should be the sum as n goes from 0 to infinity. And then maybe in the numerator, we'll have minus 1 to the n. And then we've got this descending product of odd numbers. And I believe those should start at 2k minus 1. And I see 2k minus 1 here because 2 times 2 is 4, minus 1 is 3. And then 2 times 3 is 6, minus 1 is 5. So we'll have 2k minus 1 times 2k minus 3 all the way down to 5 times 3. So that's my descending product of odd numbers. And then this is all going to be over. Well, notice that that is those odd numbers and a descending product added to 2 times n. So we'll have 2 times n plus 2k minus 1 times 2 times n plus 2k minus 3 all the way down to 2 times n plus 3. And then after that, we'll have our x to the 2n over 2n plus 1 factorial term. Okay, so now what I'd like to do is maybe prove that this is the right formula, and we can do that with induction. Notice if we were to, for instance, take fk plus 1 minus fk, we should get something that looks like our f sub k plus 2. So what will we have? We'll have the sum as n goes from 0 to infinity, and then we'll have almost exactly these terms right here. So in fact, I'll just bring all of these down. We'll have our minus 1 to the n, 2k minus 1 multiplied all the way down to 5 times 3, and then 2n plus 2k minus 1 multiplied all the way down to 2n plus 3. Then that's going to be factored out of what? Well, notice that we'll subtract 1 from whatever it's factored out of because this is the coefficient of f sub k. And then what we'll have for the coefficient of f sub k plus 1 will be a 2k plus 1 over, let's see, it'll be a 2n plus 2k plus 1. So that's the top term of those descending products if we plug in k plus 1. And then, of course, we have our x sub 2n over 2n plus 1 factorial terms that come along for the ride. Okay, nice. But next up, what we can do is put these two together by finding a common denominator. And let's observe that that's simply going to give us minus 2 times n over 2n plus 2k plus 1. And then we can do the same kind of things that we did before. Notice that the 0th term is equal to 0, so we can change that to a starting point of n equals 1. And then after that, we'll do our change of index by replacing all of the n's with n plus 1. And that'll leave me with minus 1, or sorry, the sum as n goes from 0 to infinity of a minus 1 to the n. You might say, well, now it's minus 1 to the n plus 1, but I'll do the same thing as I did before and absorb this minus sign into the 1 over here. And then I'll have 2k plus 1 times 2k minus 1 multiplied all the way down to 5 times 3. That's from my reindexing. Over, and now this thing is going to be what? Well, we'll have 2n plus 2k plus 1 times 2n plus 2k minus 1 all the way down to 2n plus 5. Notice it starts at 2, it ends at 2n plus 5 here because of our reindexing. And then this term right here will become 2n plus 2 over 2n plus 2k plus 3, again from our reindexing. And then we'll have an x to the 2n plus 2 over a 2n plus 3 factorial. Okay, nice. But now we can do the same sort of simplification we did before. We can take this 2n plus 2, cancel this 2n plus 3 factorial down to a 2n plus 3 times a 2n plus 1 factorial. We can take this x to the 2n plus 2 and factor an x squared out of the whole thing. And what we'll see pretty quickly is that this will be equal to x squared all over 2k plus 3 double factorial times f sub k plus 2. And you might say, well, what is 2k plus 3 double factorial? Well, it's exactly kind of what you want it to be, this descending product of odd numbers. So we'll have 2k plus 3 double factorial is equal to 2k plus 3 times 2k plus 1 all the way down to 5 times 3 times 1. Okay, so what we've done here is we've wrapped up this closed form for these f sub k functions that are built out of the seeds, which happen to be the cosine and the sine x over x. So next up, we'll leverage this to find our continued fraction representation of the tangent. So we just did a pretty big calculation to motivate the following recursion. And that is fk plus 1 minus fk is x squared over 2k plus 3 double factorial fk plus 2, where we have f0 and f1 defined as follows. So next up, I'd like to define this new function, which we'll call gk of x, and that'll be the quotient fk plus 1 of x divided by f sub k of x. And let's observe that the first one, g sub 0 of x, is f1 over f0, which is, well, essentially the tangent over x, because we'll have sine of x over x all divided by the cosine of x. But now I can rewrite this as 1 over f sub k of x over fk plus 1 of x. That's kind of a silly way of writing the same quotient. But now what I'll do is solve our recursion up there for the fk function. So let's see, what'll that leave us with? We'll have 1 over, so solving for the fk function, we'll have fk plus 1 of x minus x squared over our 2k plus 3 double factorial fk plus 2 of x. And then this is all occurring over fk plus 1. But what I'll do is just divide each one by fk plus 1, just to make it a little bit clearer what's going on. But now fk plus 1 divided by itself is pretty clearly equal to 1. So that gives me 1 over 1 minus, and then we've got x squared over 2k plus 3, our double factorial. And then fk plus 2 over fk plus 1 will, motivated by this definition, be gk plus 1 of x. And now we've got our seed of a method to create our continued fraction for the tangent. So let's start that on a new board. Before we continue on, I'd like to tell you about my second channel math major, which is devoted to full lecture courses in mostly upper division math classes. And I keep that whole channel ad-free thanks to my support on here via channel memberships and on Patreon. So if you'd like to help me keep that ad-free, consider becoming a channel member or becoming a patron, but there's no pressure. Okay, so we just observed that if we let gk of x be fk plus 1 over fk, then we get this nice formula that it's also equal to 1 over 1 minus x squared over 2k plus 3 double factorial gk plus 1. And now I'd like to start at the very bottom here, and that will be tangent of x over x, which observe that that is g sub 0 of x, because it's f sub 1 over f sub 0. But using my recursion right here, that's going to be the same thing as 1 over 1 minus x squared over 3 times g sub 1 of x. So that's using that recursion one time. But now using that recursion a second time, this is going to be 1 over 1 minus x squared over 3. And then we can replace g1 with a 1 over 1 minus x squared over 5 times 3 times g2 of x. Again, just using that recursion again. But now I can take this 3 and multiply it through and observe that this is going to turn into 1 over 1 minus x squared over 3 minus x squared over 5 times g2 of x, like that. But now I can continue this process on and on and on, and I come up with this nice continued fraction. So let's see, I'll write it for a while. So we have 1 over 1 minus, and then this is going to be x squared over 3 minus, and then this is going to be x squared over 5 minus, and then this is going to be x squared over 7 minus, and then this will be x squared over 9 minus, x squared over 11 minus, and then so on and so forth. So there you can see, just using this recursion right here and this nice cancellation that happens from all of those double factorials, we have this pretty cool expression for the tangent of x over x. And now what we could do is simply multiply both sides by x, and we'll have the tangent of x is equal to x over, well, all of that stuff that I previously described. Okay, nice. So now that we've got our continued fraction for the tangent function, we can go about proving that pi is irrational. So we just did quite a bit of work to land at the following continued fraction representation of the tangent function. Now we're ready to put this all together and show that pi is irrational. And we'll do this by way of contradiction. So by way of contradiction, let's suppose that pi is a rational number. But that tells us that pi over 4 is also a rational number. I think that's pretty clear. But that means that there exist natural numbers that I'll call a and b, such that pi over 4 equals a over b. So we're expressing pi over 4 as a rational number. But now we're going to use the following fact along the way, and that is 1 is the same thing as the tangent of pi over 4. In other words, the tangent of pi over 4 is 1. But now we can plug pi over 4 into our representation here, but we'll plug it in as a over b. So that means I'm going to have a over b all over 1 minus, and then this is going to be a squared over b squared over 3 minus, and then this is going to be a squared over b squared minus, or sorry, over 5 minus, and then a squared over b squared over 7 minus, and then so on and so forth. So now what we can do is maybe clear all of the denominators everywhere. So multiply the numerator and then this first denominator by b, and then keep going, but multiply by b squared in each case. And so that's going to give us the following expression. So we'll have 1 is equal to a over, and then it's going to be b minus a squared over 3b minus a squared over 5b minus a squared over 7b minus so on and so forth. Now we've got this kind of crazy continued fraction representation of the number 1. Now I'd like to observe that the number 1 is rational, so I can just say, oh, the number 1 is rational, so that means that continued fraction there is also rational. But that means if I look at the tail, if you will, of this continued fraction, what I mean by the tail is any sort of bottom part here continuing on forever and ever and ever, that's also going to be rational. So in other words, for all k bigger than or equal to 0, we have a squared all over 2k plus 1 times b minus a squared over 2k plus 3 times b minus a squared over 2k plus 5 times b minus a squared over so on and so forth. That must also be rational. So that's just kind of an arbitrary place to start down kind of near the bottom. I guess there is no bottom, but downstairs in this continued fraction representation of 1, which is rational. Thus, all of those parts are also rational. And I just realized I have the wrong quantifier here. This should be for all k bigger than or equal to 0. That thing right there is rational. And I'm going to go ahead and call this thing t sub k. Now what I'd like to do is pick a certain k such that we have 2k plus 1 times b is bigger than a squared plus 1. So that's possible. We can just scale b until it gets larger than a squared plus 1. I think it's pretty clear that that is possible. But now if 2k plus 1 times b is bigger than a squared plus 1, so is 2k plus 3 times b and 2k plus 5 times b, because those are all bigger than 2k plus 1 times b. Now what I'll do is replace each of those with a squared plus 1, and what we'll do is create something larger. And that's because we're making the denominator smaller. So it's a little bit tricky to see. Kind of obviously, if you replace only this one with a squared plus 1, the denominator is getting smaller. But then this next one is like in the denominator of the denominator, and then it's wrapped up with a minus sign and so on and so forth. But that will also cause the whole thing to get smaller. So in the end, if you replace all of these 2k plus whatever with a squared plus 1, what you end up with is something which is larger, because on the whole, we've made the denominator smaller. So this is going to be less than a squared all over a squared plus 1 minus a squared all over a squared plus 1 minus a squared all over a squared plus 1 minus so on and so forth. So again, that's just from replacing all of those with a squared plus 1. But now I'm going to leave it as a little homework exercise to check that in fact this continued fraction cancels down pretty quickly to the number 1. So what that tells us is that we can find a k so that this tk number is less than 1. Now that brings us almost all the way to the end of the proof, so let's see the final steps. So we just motivated the fact that we can choose a k so that t sub k, which was this expression right here, one of the tails, if you will, of the continued fraction, is less than 1. But in fact, not only is that one less than 1, but every one after that, if you will, is also less than 1. Okay, so now I'd like to observe the following, and that is if we pick one of these k's bigger than our capital K, let's rename all of these coefficients in our continued fraction just to make it a little bit easier. So let's set tk equal to a over b1 minus a over b2 minus a over b3 minus so on and so forth. So you can see that my capital A is just a squared, but then my b's gobble up the rest of this. And then let's recall that not only is that less than 1, but we are assuming that that is a rational number. So if that is a rational number, we can write it as c2 over c1 with c2 less than c1, and they are both natural numbers because it's a rational number less than 1. And then let's also observe that I can rewrite this as a over b1 minus tk plus 1. That's the next one in our sequence. Then I can solve this thing for tk plus 1, just doing pretty simple algebraic manipulation, and we'll see that tk plus 1 is in fact c2 times b1 minus a times c1 all over c2, and that's still less than 1 by our previous discussion. But then what I'll do is just take that numerator right there and I'll set it equal to c3. So now let's see what we have so far. So I'll just put we have so far natural numbers c3, c2, and c1 with c1 bigger than c2, bigger than c3. But then there's no reason to start at this jump from tk to tk plus 1. We could just keep going. And if we keep going, what we'll get is a sequence C sub, maybe I'll use M, all of natural numbers with C1 bigger than C2, bigger than C3, bigger than C4, so on and so forth. But it's pretty clearly impossible to have an infinite decreasing sequence of natural numbers because we'll run out of natural numbers. The smallest of them is equal to 1. Okay, so that's our contradiction. Our contradiction is the inability to create this infinite decreasing sequence of natural numbers. But of course, if we have a contradiction, that means that the assumption that we made way back at the beginning of the proof that didn't follow from our logical argument must be incorrect. And that assumption is right here, that pi is a rational number, which of course means that pi is in fact irrational. And that's a good place to stop.